So thanks for the introduction. So my talk is about a finite abstraction of real-valued functions for complete reasoning or inference. I know it's a lot of words, but I think, or I hope in the end of this talk, you'll kind of understand what they mean. So this talk I did, this work I did together with my supervisor Martin Lange and together with Florian Bruse. So generally, I want to give you some kind of idea of the background of this work, so why we actually do this. So the general idea is to work in like digitalization for like secondary education. And we want to contribute by giving like some kind of tool that students could use in class to formulate some kind of hypothesis, in this case, about natural science experiments. So the goal, as I said, is to have like in the end some kind of tool, and for that we need like the background reasoning. So this talks about like the logic behind this background reasoning. So we already contributed a little bit to this in 2023, where we had a paper where we introduced this concept and the concept of experiments, or what we consider as natural science experiments, and already developed some kind of proof calculus to like validate some kind of hypothesis. However, we did have some problems with it, as we had to restrict the kind of experiments that we had to consider, such that the calculus was actually complete. So what we did now with this work is that we try to extend this to have like a complete algorithm for this hypothesis validation. So let's start by introducing the concepts, like the general concepts of what we think or what we mean by the terms influences and especially experiments. So generally, what we mean by an experiment is simply like a collection of functions which we call influences, and such influence is typically associated with a pair of variables. So such influence typically, as I said, is a function which should describe the influence of one variable onto another one. For example, like the influence of altitude onto air pressure or something, which is simply like a function mapping real to real values. And thus, as an idea of what kind of hypothesis we actually want to formulate with this idea is given here. For example, when in between 7 and 8 kilometers of altitude does oxygenation saturation decrease while staying in between 60 and 70%. So this is the kind of hypothesis we want to be able to formulate. So let's dive into an example of an experiment, which is given here. Firstly, we have like the domain, or like the signature of the experiment, which are the variables where the influences actually talk about. So in this case, it's altitude, air pressure, oxygen saturation, and these are actually ordered as we only have like influences between variables that are within this order. So for example, we have in this graph here, we have altitude influencing air pressure. In this graph, we have pressure influencing oxygenation, and in this graph, we have altitude influencing also oxygenation. So this whole thing is an experiment which is simply like a collection of functions, where essentially the x and y axes are labeled by some kind of variable, which gives it some kind of semantics of what they should express. And there's another property to experiments. They are not only like a collection of these functions, but these functions or influence are actually interconnected in some way. As you see here, we have altitude influencing air pressure, and we have air pressure influencing oxygenation, and then we have like some kind of transitive property. So altitude also influences oxygenation via this like transitive pattern. So we have some kind of coherence property within these experiments, which basically just state that the transitive connection has to behave exactly like the function composition of these two, which is, I guess, the only viable option to handle such case. So what we have until now is like the general topic, or like the things we actually want to reason about, but these are a little too specific. So we don't want to have like exact experiments in that case. We simply want to have like a description of experiments. That makes sense for several reasons. For example, you could imagine students collecting some like experiment data in class, so they don't have the exact same data in the end, but whether they have like small errors and stuff like that. And we want to incorporate this into the framework So we don't want to reason about like actual experiments, but rather some kind of description of experiments. So this what we are doing here. So we start by some what we call inference statements, which are simply like some kind of assertions which we do where we allow or disallow inferences to behave. So, for example, an inference statement consists of 5 parts, 2 variables, 2 closed intervals of variables, and one thing what we call a behavior. But I think it's best to just imagine it like as some kind of rectangle that we draw onto this graph of the inference. So the semantics of this is basically that we demand any inference to satisfy the statement only if it is firstly defined on the domain of the statement. So the inference has to define this domain from 4 to 8 in this case. And if it's defined, then it also has to only take values within the range of the statement. So it's not allowed to go down here or something. And it has to behave like the behavior here actually dictates. In this case, the behavior has 4 possible values, and it's simply like the upwards arrow simply means, well, the inference within this domain has to behave monotonically increasing. If the downward arrow, in this case, it means it has to be monotonically decreasing. The constant error means it has to be constant, and the arbitrary error basically, this swirly error here, this arbitrary behavior, and this basically means we have no restriction to the behavior of the inference on that domain. And one important thing here to say is that both the monotonic and antitonic or decreasing behavior here does not have to be strict, so it could also be constant on the domain. So what this gives us until now is we can describe like how an inference which we want to experiment should behave on one inference on one small domain. But that's not enough to describe like a whole experiment. So what we do is rather simple. We take a finite set of these statements to describe an inference. So for example, here, our running example of this experiment, or just this part of the influence, we have like all these statements, and when does the inference actually satisfy this scheme? Well, when it satisfies all of the individual statements. And there's one special thing here: we do not allow to use the arbitrary behavior within the statements of the scheme. This has some technological reasons. So this has like 2 important properties. For one, we can actually model such given experiment with some kind of arbitrary behavior. In this case, we have like this scheme, but we could also take another scheme. For example, the only thing that changed here is that the constant error here is now a monotonic error. I just played around with the fact that, as I said, it doesn't have to be strict monotonic, so it can be constant. Or we could use like a really broad statement to model this influence. Or we could be like way more precise and have like way less room for error. I did omit like the errors here, but I think the action thing should be decreasing here. So this one part we can model with kind of arbitrary behavior. And the more important thing here for our reasoning is that each non-trivial scheme, I should say, actually has infinitely many experiments that satisfy. I just draw like 2 additional ones here, but I think it's clear. We could take like any function here that stays within these statements and is decreasing like constantly like here, and would still satisfy the scheme. So the next part is the hypothesis. In this part, in this case, I already mentioned one, and I highlighted in the red here. These are basically all properties that we've seen now. We have like some kind of domain between 7 and 8 kilometers. We have like some kind of range between 60 and 70%. We have variables with the altitude on the oxygen acceleration. And we have like decrease, which is like some kind of behavior. So this is exactly another type of statement, like a special type of statement, which we then want to reason about. So this allows us to give some kind of decision problem, given the scheme, which is basically just a description of an experiment, and hypothesis, do for all experiments that fit the description, so satisfy the scheme, also follow that they satisfy the hypothesis. So it's some kind of consequence relation. So in this case, again, I omitted the downwards error in all of these to not clutter it up too much. But in our running example, we see that it actually goes through the statement, so it does satisfy the scheme. However, and it also satisfies the hypothesis. However, we could draw like another function through this, which also satisfies the scheme, obviously, but it does not satisfy the hypothesis, and it's not within the range of the hypothesis. So the hypothesis in this case is not like a consequence of the scheme. So what we did originally was to reason about this using some kind of calculus, where essentially like combined information about all of these statements. So for example, we had like, if we have an influence satisfies a statement and it satisfies another statement and both of these overlap, then for example, the intersection of this is also satisfied by both of these statements, by both of these influences. So this allowed us to reason in some kind where we just generated new statements from existing. But as I said, this was not complete. I will not go that much into the details, but give you like some kind of hint to why that is. The problems are actually with the variable order. For example, if you have diamonds within the variable order, and it was some kind of puzzle diagram here on the right, where we simply have partial order and we clearly have a diamond. And another problem is statements over non-elementary variable pairs, where elementary means that we do not have any variable in between. For example, in this case, A and B would be elementary as there's no variable in between, but A and D is not elementary as there's like variables in between, in this case, B and C. So if we consider like the composition of statements, let me go back at 2, then we could imagine any inference that satisfies this statement composed with any influence that satisfies this statement actually has to be monotonic here. This is simply a fact because this is monotonic, this is monotonic, and then the composition also has to be monotonic. However, we have a non-elementary statement here, the AD statement, which states that it actually has to be monotonically decreasing. So if we combine both of these from the composition, we can deduce that it has to be monotonically increasing, but from the fact that we have this statement here and this E, we know it has to be monotonically decreasing. So the combined fact is that it has to be constant. So this is why I do like the small blue arrow up there. But I mean, if it's constant there, then it has to be, the reason has to be of the influence it is composed of. So in this case, it kind of introduces some kind of non-determinism, because either the influence is constant here, which then means that the composed one also has to be constant, or it could be that it's not constant here, so it actually has some kind of real range, I'd say. And if we flip this range, look at this here, then the influence in this area has to be constant there in order for the composed influence to be constant. And then we have like some intermediate constraints that are like more precise than what the statements say, and are like, it does introduce some like relative points. And this is not captured by the calculus by any means. So we try to go with an alternative solution. If you look again at this consequence relation up here, so we have that we actually have to test any experiment that satisfies the scheme and have to ask ourselves, does it also satisfy the hypothesis? However, this is clearly not possible to do, as I already mentioned. In general, we have infinitely many experiments satisfying such scheme. So what we do instead is we try to classify all these experiments in using some kind of classification, which then results in finite classes. So we only have to iterate through finitely many classes, and if each of them behaves in a certain way, such that two experiments are equivalent, if they satisfy the same set of statements and the same set of hypotheses, then it's sufficient to only check like one representative per equivalence class, and such. So we only have to iterate through like finitely many options and have to check each. Maybe I have to say this is obviously not like something that's feasible computationally wise, as this could lead to like a lot of time if we have many classes. But it's just a first idea to grasp whether it's actually if possible to find like a complete algorithm for this task. So generally, what we will do is we will introduce these equivalence relation on the influence itself, as experiments consist of influences, and then generalize this to whole experiment in the sense that two experiments will be considered equivalent if all of the influences are equivalent, which describe like the same pair of influence. So the general idea of this categorization is that already a scheme or a statement kind of categorizes influences or experiments in two parts, one that satisfies the statement and one that does not satisfy the statement. But the reasons for that are like more subtle than that. And they are actually like from the definition of the semantics of the statement. So either because they have different ranges on the area of the statement, or they have different behavior on the area of the statement, or they are differently defined on their domain. So one's defined and one's not. So to clear this up a little for this talk, we simply assume that like we only consider functions which are like total. So we don't have like the last case of the domains here. So we only have to consider like different ranges and different behaviors. So for the behaviors part, what we will do is we will actually interpret how the influence behaves on some small domain, but in this case strictly, not so loose as the statements asserted. And for the ranges, we will assume how these influences actually, what the ranges are. We cannot use like arbitrary possible ranges, obviously, because there are infinitely many, but we only have like finitely many possible ways to restrict them using the scheme, as we only have finitely many bounds. And for here, we're simply assuming to have some underlying integer grid where we simply mark, like, and I think it's best to show the next slide here, where we simply mark on what kind of area the influence actually walks through, I'd say. So in which parts of this grid are actually touched by the influence. So this is like the first idea, and this actually would work for like, such that they uniformly like satisfy and not satisfy hypothesis when they're in the same class. However, we have like big problems with the composition of these statements. And I think the main problem here can be seen like that, because I think what we have here is we have like two influences or two kind of experiments which we consider. The equal parts are colored in black here, and the differentiating parts are colored in red or blue stuff. So what we have here in the composition, that this ranges here from 1 to 2.5. So in the composition, we combine this piece of the influence with this piece of the influence from 1 to 2.5. And however, while these are like equivalent respecting the integer grid, they do behave differently on this part from 2 to 2.5, while this blue one stays constant here, and the red one goes down instantly, is increasing and has like a different range, which then resides in the composed influences to be like in different kind of classes. So we have to avoid this. The whole idea and the whole thing we have to achieve for the rest of this talk is that we actually can compose like the influences of classes uniquely, in the sense that if you take any influence of that class, any influence of that class, then you end up always in the same class in the composed case. So there's actually another problem, which is a little more technical in the sense that we cannot use arbitrary behavior that well for this reason. We cannot uniquely deduce the behavior of the composition of the influence. So we have an example here. Normally, we would expect if we have a composition of an influence on a part which does exhibit arbitrary behavior, we would accept the composition to also exhibit arbitrary behavior. However, this does not have to be the case. In this example here, we have like arbitrary behavior as it goes like up and down multiple times in between the interval of 0 to 1. However, these arbitrary cases, as colored in red here, are kind of like cancelled out by the influence we compose it with. So actually, we do not end up with an influence that has arbitrary behavior, but it's monotonic over the domain from 1 to 0 to 1. However, if we would not have this constant parts here, then it would have been arbitrary. So we cannot deduce like uniquely the class here in that case. So, however, we did not allow like the these statements of the scheme to have arbitrary behavior. So in some sense, we already have some decomposition of like when it grows and when it switches like behavior. In this case, we have like it goes from 0 to 2 here. So when composing, it goes like from this 0 to 2 and maps this to the composing composition. However, this then introduces arbitrary behavior which we want to avoid, and we do this by simply like consider when we cross this border here, as we know, between for at least for like the elementary pairs, we do know that in between integers we do not have arbitrary behavior. So if we compose like this part from 0 to 0.5, where the range is from 0 to 1, then we know that the composition is actually this part here, which is not arbitrary itself, and then we have the other part behind that. So we actually have to decompose the inferences further, such that in the end we have like, no matter what inference we compose with in the end, we do not end up with arbitrary behavior again. And I mean, I kind of gave already gave the idea of how to do this. This is a little bit bigger example. So we begin with, again, this integer grid. And then for this function, we just mark whenever we cross some kind of bound where we cross such integer bound. And then we also mark these parts. So this then means that the composition, so the BD inference, which I did not depict here, actually does not exhibit any arbitrary behavior between these points. But we could also have like another inference before that. We could also have like the AB and then the BD. So we actually have to, in this case, have to not only respect whenever we cross these integer bounds, but also these turning points, which we call them, that we collected like before. So this is some kind of top-down analysis of when we cross these set of turning points, such that we avoid generating like arbitrary behavior. And this was like the other problem, but the main problem I proposed with the example before was that we do not have like the exact ranges. So we do not have like the exact composition in the end. So what we do here is we, again, in this case, we call them, it should be points of interest in this case, what we collect, what we call them. So we actually like also collect the points where the actual function is. So we don't not only take like the integers, but like the actual points on the integers in the lower part, and then we mark again these points here, and we also collect the value of the function takes on these parts and so on. So we collect even more points, and in the end, what these classes actually look like is kind of hinted in blue here again. I dismissed like the behavior part, so there should be also in there also. But this kind of is like the class of influences or experiments we consider now. So it's like any influence that actually takes the corner points here. So this is different to like the statements I introduced before. As the range is like the exact range of the influence now. And this allows us to uniquely compose like these classes. As we know, for example, on the domain from 0 to 1, the range is 0.5 to 1. And we do know how this influences behaves from 0.5 to 1. And we can like, this works like for all possible composition of all of these functions. Yes, and what this then gives us in the end is that we are it enables us to iterate through all of these classes. It's kind of like in reverse of what I've done here. I started with an experiment and generated like the class of it. Normally, we would have to work through like each possible class individually without like having the experiment given beforehand. But this then allows us to actually have like a complete algorithm such that we can like partitionate all the set of experiments, walk through the finitely many classes and check whether like the given class like satisfies the scheme and satisfies the hypothesis. And this even gives us some kind of co-NP solution. So we do know that the consequence relation is in decide balance in co-NP. And it would be easy actually to see this when we consider like that there are only finitely many of these interesting points that we consider, and the amount of these points actually polynomial in with respect to like the size of the scheme. So what we actually can do is like guess what kind of or guess the class and yeah, then just check whether it is the counter example of the given scheme. So if it fits the scheme, that does not satisfy the hypothesis. And yeah, this is like the main result we came up with in the end. But for filter work, I mean, the biggest problem is obviously we want to like encode this in some kind of tool, which should run on like maybe small tablets and stuff like that. So it has to be efficient. So as it is, it's not efficient enough. There are like two possible ways to go from here. Either we use some kind of SMT solvers to encode this problem and actually solve this and like do the class search, or we try to give like a hypothesis-driven approach where we maybe have some polynomial time algorithm. And yeah, there's like way more general stuff to do. We could extend the experiments to have like multi-variable influences where multiple variables influence another variable or stuff like that. And we have like to do a lot of infrastructure of tools to actually use this kind of stuff. But yeah, so that's my talk. Thanks for listening. Thanks.